Okay, so as I mentioned, today's pretty pivotal because we learn about some basic rules which will make taking derivatives much easier. So the question is, well, why didn't we learn this first? The answer is, it's important that you understand the conceptual part of a derivative. If we dove right into the stuff we're going to do today, you will have lost that conceptual part, which is very important to the whole process of taking derivatives. So we're going to talk about how to take a derivative. We're also going to go back to that e to the x thing. Just a quick question, what's e equal to? Anybody remember?
2.71.
Nobody remembers.
Oh, wait.
Okay, let me get
Yeah,
it.
it's $20 bill. Right, so
2.718281828459045.
Yeah. Right. $20 bill. Jackson's the 7th president. He was elected in 1828. He ran it for a second term, 1828. When he folded up, he did 45.90. Right. Nobody cares. Well, that's good. Okay, so we're going to talk about the constant rule. Constant rule, easy peasy. Power rule is huge. And all of this stuff that we do with derivatives over the next couple of months is going to boil down to the power rule. And the difficulty, I won't even say difficulty, the applications of derivatives are going to be just learning more and more tools to take derivatives. The first and most important rule is what's called the power rule. Constant multiple rule is easy, and we'll talk about sums and differences. You can pretty much guess what's going to happen there because it fits the model of everything else. The derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. We're going to find the derivative of e to the x. I don't have anything else for you, so I couldn't come up with anything at the end, unless you do. What should be our last thing on a Monday? You should be able to take a nap. Excellent, I love it. Not during third block. Some other time other than third block. Cool, I like that. All right, constant rule. What happens when you take the derivative of a constant? So let's suppose we have a function y equals 7. What's a derivative of y equals 7? Why? Why?
Well, you do the definitions with it. I don't know, it's zero.
Yes. We could assume that the function is 7 and plug into the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. But there's an easier way to approach this. What can you tell me about the graph of the function y equals 7? Andrew,
Slope is 0.
why?
It's a line on y equals 7.
What kind of line? Don't say straight. All lines are straight.
Horizontal.
Horizontal,
Yeah.
right. This is a horizontal line at y equals 7. What's the slope of a horizontal line? As Andrew mentioned, it's 0. Any horizontal line has a slope of 0. Well, what is a derivative? A derivative is the slope of the tangent line. So we would get 0. So you could go home, for those of you that are memorizers, you could go home and just memorize, anytime I take the derivative of a number, I'm going to get 0. Or you could try to apply the concept here that we're dealing with a horizontal line, and horizontal lines have a slope of 0. And that's what that says. The derivative of c equals 0. Now let me talk a little bit about the notation here. I talked about the difference between something like y prime and dy dx. Okay, so what is the first one is just a notation that we started with the function y, and when we take the derivative we get y prime. Easy. The bottom one, what is the derivative of y with respect to x? X is our variable. How did it become this? Well, I know what my function is. My function is c. So this is what is the derivative of this function c with respect to x? So you could have something like this. Okay, just to make sure you're okay with the notation. The y gets replaced by the function. And again, it gets a little confusing when we bounce back and forth between two different notations, but that's a fairly common practice, is being able to bounce back and forth between the two. Okay, any problems there? Make sense? Yes or no? Yeah? Okay. See a couple of kids. Oh, yeah, look at that. It's in there too. All right, so we did that one already. Y of 7 is 0. Great. The derivative of 0 is 0. Okay, the function y equals 0 is the x-axis. It has a slope of 0. Negative 3 is 0. And you can see I'm beating a dead horse here, but I did want to mention, what about the derivative of pi squared? Pi is just a number, so therefore its derivative is 0. Okay, that's the easy part. Now, let's get into the power rule. This is going to be fun, and it's going to make your life a whole lot easier. So there's the power rule. I'll explain how to use it in a second. I'll give you a second to write it down. If you're taking the derivative of a polynomial x to the nth, the derivative of that would be n times x raised to the n minus 1 power. Spent some time working on my transitions this weekend. Okay. Yep. 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 And since the Bears game was such crap, I have 2 of them in this slideshow. So there's the first one. The other one will come soon. Okay. Now, following this rule, I don't necessarily like this rule because it's in fancy calculus speak. But if we take something like x squared, what's the derivative of x squared then?
2x.
2x. Bring the exponent down, reduce the exponent by 1. That's probably more realistic than that gunk in the purple box. Okay, I'll say it again. Bring the exponent down, reduce the exponent by 1. Bring the 2 down, reduce it by 1. 2x to the first. And we're, yeah?
It was like 2x squared, but then it would be like 4x.
Oh, we'll get there. Yes, yes. Yeah. Slow your roll. All right, so x cubed. Maria, what's the derivative of x cubed? X, there's oh, which Maria? Sorry, you Maria.
3x squared.
Bingo. That wasn't hard, was it?
No.
Good. What's the derivative, Jacqueline, of the cubic root of x? You're going to have to explain that. Where'd that come from?
It's x
No. That's not x to the 2/3. X to the 1/3. Okay. So this is the same thing as x to the 1/3. So then what did you do for the derivative? What would it then be?
So it would be 1/3 x to the power of
Bingo. This is the, let me get rid of that mess in there. This is the same thing as x to the 1/3. Bring the exponent down, reduce it by 1. 1/3 minus 1 is negative 2/3. Now let's talk about this step. Right now I don't care about that. You can leave your exponents as negative values. At some point, when we get comfortable with this power rule thing, the last thing I'm going to ask you to do is to get rid of negative exponents, but that comes later. For now, just stop at this bad boy. That's good enough. If you're feeling fancies in your panties and you want to get rid of the negative exponent, then by all means, go ahead. Giselle, your turn. Why?
Because the like h of x is x squared.
again, you could stop here. For now, that's okay. Was it your group that had x cubed, Eunice?
Yeah.
So you saw the monstrosity for taking the derivative of x cubed when they put their, it wasn't that bad, it was doable. But when you look at what they did on the homework versus what you can do now, I would understand if you were angry. But you'll get over it. So, now we talk about the question that Mia asked. Mia asked, what if, go back here, you asked if there was a 2 in front of the x squared? Yeah. So that is applying the constant multiple rule. If you're taking the derivative of a function times a constant, it's the same thing as a constant times the derivative of the function. All right, so for discussion purposes, I'm going to write it as 3x squared. Let's suppose we're taking the derivative of 3x squared. That's the same thing as 3 times the derivative of x squared. We did that already. That's 3 times 2x, which gives me 6x. Just because I stick a constant in front of a function isn't going to cause me to vapor lock, and in fact, we're going to change the way we do things. When you bring that exponent down in front, multiply it by the coefficient. 2 times 3, 6. Reduce the exponent by 1. 1. 6x. Okay, so we don't need all those other steps in there. I just wanted to show you where that comes from. And the fact that it has a fancy name, the constant multiplication rule. But who cares? Just multiply the exponent times the coefficient, you're good. So, you get that. Like I just showed you. 2 times 3, 6, reduced by 1, x. X to the negative 1. Down in front, that, and then I think, oh no, I thought I had one more. Okay. Hopefully this is sinking in, so I don't want to continue to go over things that are fairly easy. I've talked about this already. This idea is the fancy way that's going to allow us to take the derivative of big, long polynomials. All we have to do is just break it into each individual term. So if I have to take the derivative of a polynomial, I just take the derivative of each term and then add them up. There's the fancy edu-speak, or the calculus speak, if you will. But it says the derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. Which means that we can now easily take the derivative of f of x. Chris, your turn.
Let me think.
Okay. There's no rush. We're not going anywhere.
So, you could do the derivative of each variable.
Love it.
So it'd be 2x or 3x squared
You're off to a rip-roaring start.
minus
Uh-oh. We haven't talked about that, have we? How do we take the derivative of negative 4x? What's the exponent on that x? 1. So what would be the derivative of negative 4x? Chris?
4.
Hmm?
Negative 4. It'd be 4 x cubed. It'd be 1. Oh, it'd be 0.
That's coming out. What kind of term is this? Constant, linear, quadratic, cubic, quartic, quintic, hextic, sectic, octic. Nope. It's a linear term.
Linear.
What's the slope of that line?
4 or 1.
Got a negative sign out front.
Oh, negative 1.
Negative. Negative 4. So therefore, the derivative of that would be? You just told me. Bingo.
It's all really new to me.
I understand, it's new to everybody, except me. All right, you're almost done.
And then
Minus 0, which we're big people there, so we don't need it.
-0.
Okay, beautiful. Does it follow the model I already outlined? I started with a cubic function. Did we end up with a quadratic function? Yes, so we're good to go. Excellent. That's what I got there. I agree with you, Chris. Good job. All right. Bryce, your turn. It's a good start. Minus. How do you do?
I think pretty good.
All right, we're going to go with it then. Well done. Quartic becomes a cubic for the first term. The second term is a cubic. It becomes quadratic. The third term is a linear term, which becomes a constant. Okay, so anytime you take the derivative, again, you're reducing the degree by 1. Okay. Now we take the next step. And the next step is to ask a simple question. Where does this graph have tangent lines that are horizontal? Andrew, what can you tell me about a horizontal line?
It has a slope of 0.
Has a slope of 0. So we want to know where is the derivative equal to 0 for a graph like this. So bust out your Desmos or your calculator, graph that and see what it looks like. Before we start doing the work, I would like you to tell me how many answers should I expect to get?
You gave it.
Never mind, I gave you the graph. Got a little overzealous here. Okay, so Max,
Yes.
how many answers would I expect to get in this problem? How many spots on that graph do you think the tangent line is horizontal? Donde? That's Spanish for where?
Yeah.
Didn't know if you were taking Spanish or Italian or German or French or
Yeah.
Mandarin or, I don't know, what, do we teach Mandarin anymore?
I don't think so.
I don't
No?
know.
What
That'd
do we
be
got?
like
Spanish, French, and is that it?
Italian.
Italian.
Yeah. That would be cool.
We used to teach Mandarin.
I think you can do it like rolling meadows.
Oh, you have to go somewhere else.
Yeah.
Oh, I guess we're not good enough. Okay, back to you.
Donde is the question?
See?
Alright.
Approximate values are okay.
Okay. Y equals 4.
Give me the x values.
X equals 2.5,
Okay, keep going.
and X equals negative 2.5.
So are you taught here? I don't want to guess. Come here. Put on a dot on the graph where you think the tangent line is equal to 0.
Like here and here.
Okay, why would you say there and there?
Because that's like goes like as far.
Remember, we want tangent lines that are horizontal,
Oh.
not vertical.
Yeah.
Vertical, horizontal. Don't know. Anthony, catch. Where are the tangent lines horizontal on that picture? Just there? Ooh, just there? Uh-oh, 3. 3? Or 3? You're going with 3. 3, do we agree? Okay. Looking at the picture then, I would agree. We'd have one tangent line there, we'd have one tangent line there, and we'd have one tangent line there, with a slope of 0. So how do we find them? Well, we start by taking a derivative. Let's take a derivative. Luke.
Hi.
Hi. What's f prime of x, please?
4x cubed
It's a good start.
minus 12x.
Are you sure?
I think so.
Okay, good. Just checking to see if you're paying attention.
That's it.
Okay, good. So there's a derivative because the 4 goes away. Very good. And again, going back to the question, where is the tangent line equal to 0? Remember the derivative, I'm going to say this 1,000 times until it burns into your melons. The derivative is the slope of the tangent line to the curve. So we want that value to be equal to 0. Okay, solve that please. I'll wait. Allison,
Yeah.
what's x equal?
Plus or minus square root of 0.
Well done. Does that match with the picture? Yeah. What's the square root of 3, by the way?
Not 1.9.
No.
Something between 1 and 2.
Outstanding. Do we have an answer between 1 and 2? Yup. Yup. It's actually 1.7 something, I think. Excellent. Okay, make sense? Now, that's by far the most common type of tangent line question they will ask. However, they will occasionally just say, where's the tangent line to this curve equal to 1? Or 7, or negative 32. You can set that equal to whatever value that you want, but I know where we're going, and this process is something that happens a lot as we move forward. Because those become, well, you can see, the horizontal tangent lines become the hills and the valleys of the graph, which is what we're going to be looking for later. Questions so far? E to the x. Now, we don't have enough calculus right now for me to show you why this is the case. And the proof right now is really, really ugly. So you're just going to have to trust me on this one. The derivative of e to the x is itself. And as far as I know, that's the only function where that happens. Here's your second transition for today. Looks like it's coming right at it, doesn't it? You're welcome. That took me about 3 hours. My wife's very good. Could have not mown the lawn. But no, nothing but the best for you guys. Okay. Now, we're going to get all fancies in our fancies. So not only am I asking you for the first derivative, but since you've proven that you can take that first derivative, I'd like you to then find the second derivative. So, forget this function for a second. Suppose I started with a cubic. I take the derivative, I get what kind of function? Quadratic. I take the derivative of a quadratic, I get a linear. I take the derivative of a linear, I get a constant. I take the derivative of a constant, I get, and I take the derivative of 0, I get 0. And you see that eventually it goes down to, anytime you take a polynomial, no matter how high the degree is, if you take the derivative enough, you'll get down to 0. This is not a polynomial. So go ahead, find the first derivative and the second derivative. Compare notes with your table mates.
You do the x and then the negative.
Minus
That's what we got.
Huh?
I mean, like,
Oh, well, I guess the road just had a little trouble.
wait, don't go anywhere. Bonus question, what's the third derivative?
Well,
Same thing?
Shh, quiet.
Always like that.
What about the fourth derivative?
Just keep it right.
Yes. Who's the fifth one?
Fifth derivative. How do we zero? Fifth derivative.
Hey, what's the fifth derivative? I know what it is, Patrick wanted to know. Toby opened this. Excellent, okay, let's give it up for Jaeger. Now, notice,
You're right there.
no, to the left. See the little rectangle there?
The right side of it.
Oh,
Nice.
that's crazy.
You'll notice that as we continue to take the derivatives, we get more and more apostrophes. That gets to be a little tedious. So as far as notation goes, once you get past the third derivative, which you seldomly if ever will, you can change those 4 dashes into the number 4. Okay, so if we were taking the 9th derivative, for instance, which I was thinking about having Jaeger do, but that was just, then I'd just be a jerk. It'd be f to the 9th of x. Now, that seems to contradict what I said before, because what I said before is if we start with a quadratic, it will, or start with any type of polynomial, it will reduce down to 0, but this, however, is not a polynomial. It eliminates all the other terms when we get down to that. Questions? Seems like an easy process, yes?
Yes.
Okay. Think we're done. Now, from this point forward, a lot of your homework is going to be mechanical. By that I mean, here's a function, take the derivative. That's what a majority of your homework looks like. So what I'm doing moving forward, I hinted at this last week, is I'm going to spread things out a little bit because you need to get in and get your hands dirty and try these problems. Most of them are straightforward. Occasionally something will pop up where you're like, well, how the heck do I do that? And that's where we start to get into these conversations, so that my goal is to expose you to as many types of different problems as possible, so that no matter what gets thrown at you, you can take the derivative of it. So today, we're done for today. Tomorrow, not tomorrow, today's Monday. On Wednesday when I see you, I'll teach you another lesson. And that lesson will allow you to, it doesn't matter what it is. But then on Friday, we'll do an amalgamation of both days 13 and 14. Okay? So day 14's homework will be the back end of this stuff, and then the front end of the next lesson. And then Friday will be all the back end stuff. Okay? Make sense? Yeah. There is not. I haven't created one yet. I will do that once you get started. Great question. Okay. Anything else? I'm sorry? Where? Oh no, that's me. I would love to blame it, but I do the slideshows. You think ever could figure out something like this? I mean, there's no way. I mean, that took me hours. And I'm a seasoned veteran. A young guy like him could never do that, let alone this one. I mean, that's just not going to happen if you miss Mr. Evans. So I will take the hit on that. I won't admit to it very often. All right, use your time wisely.